short-term training program on applied computational fluid dynamics for automotive, space and defense sector, sponsored by AICTE under AQIS. Our today's session speaker is Dr. Chetan Mistry sir. He is an assistant professor in Department of Aerospace Engineering at IIT Kharagpur. He has completed his B from SV Regional College of Engineering and Technology, Surat in 2000. Then he did his ME from National Institute of Technology, Surat from 2001 to 2003. He did his PhD from IIT Bombay in the period of 2010 to 2014. His research areas include CFD study of turbo machine, contra-rotating axial flow turbo machine aerodynamics, electric propulsion, the computational fluid mechanics and heat transfer, and in experimental aerodynamics. He is involved in establishing up the turbo machinery research facility at the Department of Aerospace Engineering. He has published 8 research journal articles in various international journals and also published around 30 conference articles at various international conferences. He has also published a book on proceedings of the National Aerospace Propulsion Conference in Springer, Nature, Switzerland. He had been awarded an award for excellence in thesis work at IIT Bombay. He was also awarded IGTI Young Engineer Travel Award at ASME Turbo Expo 2013 at San Antonio, Texas, USA. He has also delivered various expert talks in reputed universities. He has also reviewed various research articles for elsewhere and other well-known publications. He is guiding 4 PhD scholars. He has guided around 13 MTech students. Thank you very much, Chetan Mistry sir, for accepting our invitation and being present in this today's session. You can start your presentation now, sir. Thank you very much.
Yeah, Professor Thakkar, thank you very much. You said a lot. I don't know, I'm not that big guy. Okay, let's see. I'm sharing my screen. I'm sure you all can see my screen now. Is it visible to you all?
It is visible, sir.
Yeah, fine. And my voice, is it okay?
Yeah, it's okay, sir.
Fine. So, as introduced by Dr. Thakkar, let's see. I'll be giving my talk on, application of CFD for the development of experimental facilities. So if you look at my profile, I'm not at all straight person who is involved with CFD. I'm an experimental guy, but I cannot deny the use of your tool, that's what is called computational fluid dynamics, for the development of various experimental facilities. So here in this talk, I would like to discuss more insights of what all developments we have done using this CFD tool, and that's what is fitting well. When I received the invitation from ADIT, I say, okay, this is what is a very good topic. Let me deliver to the participants. They will get the benefit of that. Okay, so let's see. So introduction part, let me leave that part. Now, in terms of my outline for the presentation, it will be more in sense like introduction part. It will say like what exactly are you looking for in terms of use of CFD, why we are looking for this use of CFD, and how you can use this CFD for the development of various facilities. Okay, I'll be showing different case studies addressing present demanding aspects and ongoing research activities at IIT Kharagpur. That's what is more related with this topic, and we can have interaction session for that. Okay, now let me tell you, this is what is with aerospace engineering. And since I'm dealing with, aero engines, so I'll be focusing more in sense of these facilities. Okay, if you look at in terms of, aero engines, you can say we are having broad classification, air breathing engine and non-air breathing engine. In sense of, air breathing engine, we will be focusing more in sense, or we are working presently more in sense of gas turbine engines. Okay, if you look at this gas turbine engine, again, it has been classified, turbojet engine, turboprop engine, turboshaft engine, turbofan engine, most recent engines like unducted prop fan, ducted prop fan. So many of you may be having background of that, and I will try to put something so those who are having background of mechanical engineering or other streams, they also will get some feeling and will get the idea of. Okay. Now when we are talking in terms of say turbofan engine, so that's what has been classified broadly in different ways, say maybe high bypass ratio engine, low bypass ratio engine, mixed flow configuration, unmixed flow configuration. Like it itself is a big domain. So what I want to convey here is, say, all application of gas turbine engines, you can understand this, all are the applications. So majorly if you are looking at, we are having say commercial aircrafts, we are having fighter aircrafts, we are having weapons, we are having missiles, okay, we are having say space applications, we are having say land-based power plant. All those, they are mainly been working on the principle of say gas turbine engines. Okay, let me show you, it will give you some idea of here. If you look at, like basically for aircraft, the main concern, that's what is called say thrust. Thrust is nothing but the exhaust, that's what will be coming out from my engine. Okay, now here in terms of component, maybe in later slide I will tell you, but here you can understand, say this is what is my engine, this is what is called core engine. Here also you can see this is what is called core engine. The front side, that's what is called fan. Okay, it may be say small size fan or it may be big size fan. Accordingly, that's what is been classified as a low bypass ratio engine, high bypass ratio engine. Okay, so in order to improve the thrust, you can understand, say during 1940s, during Second World War, people, they were thinking of using aircraft for their special purpose, say for fighters. Then later on they realized, if we will accommodating our bombs or bombers along with, then it required large amount of thrust. That's what has given idea like improvement in terms of engines. Later on, people, they thought like in place of using this for fighters, let's try for say commercial aircraft. So there were small aircrafts. Now if you look at today, say what we are having, all this A320 or say 777 Boeing, what we have, they are having large passenger carrying capacity. So you can understand, in order to carrying all those passengers along, you need to have very large engine, big engines, and that's what we say high bypass ratio engines. So here if you look at, these are some of the products, we can say it's by Pratt & Whitney, this is what is by GE, this is what is say Trent engine. If you look at, say in sense of understanding, you can see here, this is what is a big size fan. Then later on this stage, that's what is called say LP turbine. This later stages, that's what is called say HP compressor. Here we are having HP turbine, here we are having say LP turbines. So just try to understand, suppose say I'm using this gas turbine engine for my purpose of say aviation, but the whole purpose of this engine is only to generate the thrust. Okay, when we are talking in sense of say land-based power plant, so for that land-based power plant, you will be having later on one power stage or say power turbine that will be connected with the generator, and that's what is used to generate the power. Okay, now here if you look at, I have classified as say LP compressor and HP compressor. Just try to understand, LP compressor means its operating pressure is lower. Here, like there are number of stages, that's what is been comprising of. Okay, so say this is what is comprising of rotor and stator combination. Here also you can see rotor and stator combination. Similarly here for these engines you can see. Okay, now here this is what is say high pressure compressor. That's what has been rotated with your HP turbine or say high pressure turbine. This shaft, like there are two concentric shafts. This outer shaft, that's what is called high pressure spool. The inner shaft, that's what is called low pressure spool. High pressure spool that will be rotating at high speed, and low pressure spool that will be rotating at low speed. Okay, so at this moment, this is what is by requirement. So let's try to understand like what all are the requirements by this engine. So you may be knowing, when we are developing the engine, it will take, say earlier it used to take 10 years for the development of one engine. Now these days people, they are doing whole development activity within 4 or 5 years because of they are having great competition. But like before making or before putting that into operation, what they need to do is they need to do the testing. And once they are certified with the testing, then only they can accommodate that engine with the aircraft. Okay. Now, in sense, what all we need to do is we need to do the testing. What all kind of testings we have? We can say we can have engine thrust test, engine air mass flow rate, fuel consumption. Then we need to have, say, effectiveness in terms of acceleration or deceleration. Also, engine stability. We need to have, say, vibration level, shaft, noise, exhaust. All these things we need to test when we are getting the certification. So we are not doing any kind of certification, but you can understand this is what are the requirements. Now here, if you look at, these are the test bench, those which are being used in order to do the measurement or in order to check with the performance. What all parameters they are using, say they need to have testing, say here if you look at, there are lot many cables and pipes, that's what is going to the control room. They all are connected with various sensors. It may be pressure sensor, maybe say temperature sensor, speed sensor, vibration sensor, airflow, all those things. Now, you know, like you need to do the testing on ground. It may be possible you need to do your altitude test. Maybe you need to do on your ram air testing, or maybe you need to do icing or bird ingestion kind of thing. Let's see, say this is what is one of the video I have taken from YouTube. Just try to understand this part. So this is what is a certification testing, that's what is going on for, say, Trent 900 engine. This one engine itself, it cost in billions of dollars. Okay, so this is what is another kind of testing in which one of the blade they will be removing during the operation. So many times, because of flying hours, because of the properties of material, it may be possible that may be having this kind of failure. So they need to test that. You can see this is what is a bird ingestion. Like in India also we are having such kind of failures. You can look at, this is what is a weatherproof testing. So all kind of, you know, this is what is with ice testing. This is what is icing test. Because you can understand the aircraft what we are using, that will be working on all worst kind of situations. Maybe heavy rain, maybe very heavy, say, ice, or maybe thunderstorm, or maybe very high temperature when we are talking in terms of Middle East regions. Okay, so let me move next. Now the question may arise in our mind, like why we are doing measurement? What is the need of measurement? What it says like to measure is to know. If we cannot measure, then you cannot improve. That's what is a fact. it may be any parameter. So what Lord Kelvin he told, like when you can measure what you are speaking about and express that in numbers, you can say you know something about it. So we cannot speak anything in air, open air. Okay. Now the situation is, like if we look at what all industrial problem we are looking at, that's what is having say turbulent flow. Okay. Now in all situations, if you look at, we will be having say turbulent flow. It may be having 3D nature. It may be having vertical structure, diffuser flow. Okay. And if we are talking in terms of doing all this kind of what testing we have seen, if we are looking in sense of doing by using CFD, you can understand you need to solve your Navier-Stokes equation, and that will be very difficult or maybe impossible to solve. So you can say measurement is the easier way to do this part. Okay. Now suppose say we are talking in terms of say compressor testing. So here if you look at, we are having LP compressor, we are having HP compressor. Okay. Now, like this is what is called performance map. So, your whole compressor stage, all stages, they are being designed for one particular condition. So that condition is nothing but it's a maximum thrust condition. So when you are taking off, that time you need maximum amount of thrust. When I am flying at cruise condition, you can understand my thrust requirement is lower. That's the reason my pressure ratio requirement is lower. And you can say my compressor speed, it is lower. So you can say you are operating under different conditions. What are the conditions? Maybe different speed condition, different mass flow rate condition, different pressure condition. And you can say at the same time, you will be having different efficiencies because it's working in a different conditions. Okay. Now, what all we need to do, suppose say if I say I want to do the testing for the compressor, I need to check with what is total pressure because I want to have pressure ratio, what need to be the mass flow rate, what need to be the temperature, all these things, that's what we say we need to measure. Now, like when we are talking in sense of say fundamental equation for the compressor, the work done, that's what is given by UCA into say CW2 minus CW1. Now let me tell you, say aerospace industry, it's a booming industry in sense it has given all thought process what people these days they are talking in sense of say when we say compactness. So idea for compactness that has come from aerospace. Okay, idea of lightweight that has come from aerospace. Okay, so what all you are looking for, say you are asking bags also lightweight, you say it need to be compact. So that thought process that has come from there. Now there are specific reason behind having this many number of stages for the compressor. Now what thought process has come, you can understand. Suppose say I want to have compact engine. So if I say compact in the sense my size will be reducing. I say it need to be lightweight, that means I need to have less number of components. Okay, all these things, that's what is possible only when we are doing something like I will be getting more amount of compression that will be happening per stage. So stage, I say this is stator and rotor. So if one stator rotor combination, if it is giving high pressure rise, then you can say number of stages requirement that will be reducing. Now the problem is, say my inlet pressure here and my outlet pressure at the stage, you can say since it is rising by pressure, so you can downstream pressure is higher. And that's the reason why it is working under adverse pressure gradient. Okay, when you're having adverse pressure gradient, you can understand you will be having more chances for your flow to get separated. This is what I'm saying in sense of aerodynamics. And that's the reason why it is putting constraint. But you can understand now the requirement is such, people they are asking for compactness, people they are asking for lightweight. So you need to think some alternatives. And in order to do all those aspects, you need to do the testing. Okay. Now here if you look at, suppose if I consider say HP spool. For a HP spool, that's what will be rotating approximately in the range of 12,000 to 18,000 RPM. So you can understand that part. It is rotating at very high speed. Suppose you will be having higher speed, you will be having very high stresses. At the same time, your power requirement will be very huge. Let me tell you, for one of our experiment we checked with, say for one stage of HP compressor testing, it required 3 megawatt power. So that's what is equivalent to full consumption of IIT Kharagpur. So you can understand that part. Now, since it is rotating at very high speed, it will be very risky. People will not be going near to that rig in order to do all kind of inspection testing when it is running. Now, at the same time, being experimentalist, we can say, like, we have constraints with the probe. You can understand when my flow is entering at high speed, there may be possibility that I need to use the probe that to be of smaller size. Where will I put it? What need to be the accuracy for those sensors? What about the cost? Because you need to acquire the data, maybe pressure, maybe in terms of velocity, all those data you need to acquire. Then you can say it is difficulty in measurement of detailed flow field. So if I say my one blade is rotating at 12,000 RPM, so 12,000 divided by 60, so that will be the fraction of time you will be having. It may be in microseconds. So you need to capture the flow details in that speed range. That's what is very difficult. It may be possible that you will be having shock and shock boundary interaction because your flow is high speed flow. Now the question is, do we have any alternative for this? It says like maybe we can go with the CFD. Second option, it says like maybe we can use the experimental facility. Now in sense, when I say CFD, in my language, I used to say this is what is a colorful display, because until and unless you understand the basic fundamentals of CFD, whatever boundary conditions you will be putting, it will give you some output. Okay, you will be happy looking those colorful pictures. But like when in actual condition, when you are doing that work, it should give what you are expecting. And that's what is possible with expertise, with say number of years of experience, what kind of solver you are using, how flow physics you are understanding in sense of inlet and outlet, all those things, that's what is playing very important role. Now next option what we have is the experimental facility. But as I told, my talk, it is more in sense of correlating this CFD and say experimental facility. Okay. So what we will be doing, like I will put point here, say I will be using this CFD as a tool for the development of experimental facility. Once the experimental facility will be developed, I'll be having my whole experimentation. With those experimentation, I will recheck or validate my code, saying like whether it is giving or is it captured in perfect details. Because you can understand when I say experimentation, it's very expensive affair. Because single probe, multi-hole probe for the measurement, it may be costing say 8 lakhs, 10 lakhs. When I say we want to use say hot wire anemometry, that's what is costing around 80 lakhs. You say, sir, we can use PIV. Yes, that's what is costing 4 crores. And that's what is only instrumentation I'm talking of. What about the rotor? Say single blade for the compressor, maybe high-speed compressor, it may be costing in terms of lakhs. It may possible single rotor may be costing in crore. And that too, you need huge power. You need the trained persons. Okay. So all these things, that's what we need to take into consideration. So if that's what is the situation, you say, sir, better we avoid the testing. But that's not the case. We have other alternative. That's what is called, say, low speed experimentation. What it says, since we are operating at low speed, we will be having lower stresses. Power requirement also will be lower. Maybe risk in sense of what we are saying as an interaction with human, that will be lower. Like you can have say better measurement possibilities. You can have probe size, placement, accuracy. So all these things that will be in your hand. Okay, ease in terms of measurement, no shock or shock boundary layer interaction. You will be having, you can accommodate the sensors within the blade. That's what is very important part. Okay, so like this is what we are doing here at IIT Kharagpur in sense of having experimentation at low speed. You can understand if I say this is what facility I want to make here in terms of high speed, it may cost me 20 crores for the development of that facility. I'm saying, and then after, like all things what I'll be putting together, I need to have trained person who can handle this kind of possibility. And in case of accident, it may be possibility that I may be having casualty. That's what is not permitted. So, you know, like as a poor person, you can say, we are targeting this kind of low speed experimentation. We are happy with this part. But, you know, like this low speed experimentation, what we are doing, there are some techniques with which you can incorporate what you are observing here in low speed, that you can apply those results to high speed. That's what is called skill. Okay, so question may arise, how exactly does need to be done? Okay, so what it says, you need to use the advantage of, say, aerodynamic similarity. When I say aerodynamic similarity, that means you will be having two parameters that will be coming into the picture. One, that's what is, say, Reynolds number, and second, that's what is, say, Mach number. So when I am talking about Mach number, you know, this is what is very sensitive issue. Okay, when we are talking about, say, Mach number, say, angle of attack, camber, maximum thickness, all these things, that's what is changing your Mach number distribution. So you will say, sir, like this is what is one of the constraint. Yes, this is. Next, you know, like what surface roughness we are talking of. Suppose if I say for high speed compressor, I can have few microns surface roughness. What I will be making for low speed experimentation, maybe it may be having variation in terms of, say, roughness. It may be possible to, what flow we are simulating, that turbulence intensity or Reynolds number may not meet the requirement. Okay. Additionally, you need to be very careful with the solidity and the parameter, that's what is called aspect ratio. Let me tell you in a small way, say when I say aspect ratio, it is nothing but height to chord ratio. So height of the blade by chord ratio. Okay. So all these parameters we need to take care of. So you will say, sir, like these are the constraints and what to do. But yes, we have solution for that. What we need to do, it says, like you need to follow the systematic approach. What it says, low speed aerodynamics model for high speed core engines is designed and fabricated. It can be designed with using, say, aerodynamic similarity. What you need to take care, you need to take care of solidity, you need to take care of aspect ratio, reaction, maybe Reynolds number, say your surface distribution, clearance to blade height ratio, axial spacing. Okay, this need to be in line to what you are doing for, say, high speed testing. Now what it says, like baseline blading, that will be testing, you will be finding what is the region where you will be having higher losses. That's what is happening and how it is happening. That's what is possible. You can do with great accuracy using low speed, because your sensors you can put inside the flow. That's what is giving you what you are looking for. If it is a high speed, you know, at the same time, because of high speed, your data acquisition system requirement, that also will be high speed. So it may be possible that you will not capture what physics you are looking for. Okay, so this is what is possible. What you need to do, you are identifying the region where you will be having higher losses and just try to find out the mechanism for that. Then, you know, once you identify that location, you can do modification, what we are saying in sense of, say, maybe you need to change the shape of your aerofoil, maybe end walls. You need to, because you are looking for the improvement in sense of overall performance. That's what is in terms of reduction of losses and improvement of stall margin. Okay, there are different innovative methods. That's what you need to incorporate. It says custom tailored aerofoil. Let me tell you, like, since this is what is a time constraint here, that's the reason we are not discussing in detail. But you know, initially when you are starting with your design, that time you need to have your standard aerofoil available with you that need to be used. Using your computational tool, you need to understand like how you can do the custom tailored aerofoils. You can make your own aerofoils in order to make your rotors, in order to make your stators. It says like orthodox wall geometry. I will show you what is that. Maybe you require, say, bleed or liquid scheme. All those things what you need to incorporate. Now, once you got all the details from low speed testing facility that you need to incorporate for high speed facility. Okay, let me tell you in world, if you are looking for, say, big giants, say maybe GE, Rolls-Royce, Pratt & Whitney, maybe Siemens, all these people, they are having their low speed testing facilities available at different universities. So they are not doing that research especially on low speed testing. Say professors or say students, those who are doing say BTech, MTech, PhD or PDF, those people, they are doing those kind of research. And based on this experimental, low speed experimental result, they are putting some correlation, and that's what is being transferred to high speed application. Now, as we were discussing, we are having problem with the shape of the aerofoil. Okay, that's what is maybe what, you know, like when you are doing your experimentation, suppose say on the high speed test rig only, there are high speed test rigs also available. So if you look at for India, say NL, Bangalore, GTRE, they people, they are having high speed testing facility also available. But you know, like small change if they want to do in terms of say shape of the blade, they need to remake whole rotor. Maybe they need to remake whole stator. And as I told, that may be costing very high. Okay, so that's what is a constraint. You can say we are having problem, we are having disadvantages in terms of we are unable to capture the change in flow physics because of shock waves or maybe shock boundary layer interaction. But let me tell you, when you are talking about say middle stage, in the sense say what compressor blades we are putting on say rear stages of compressor, core compressor, then you know you are not having your flow to be transonic or supersonic. Now let me tell you what is the reason. Because your already compressed air, that's what is coming out from your LP compressor, that will be entering inside the HP compressor. Now since my pressure is very high, you can say my density and temperature also will be high, and that's what is giving you your Mach number to be lower. So you can say your flow through this core or rear stage of engine compressor, that is maybe subsonic or high subsonic. So you can say this kind of facility you can easily incorporate for your core compressor testing. Okay. Now, you know, like it's well said, like the theory is something nobody believes except the person who made it. That's what has been quoted by Einstein. But when you are saying it's an experiment, that is what is something everybody believes except the person who made it. That's what is the biggest challenge in the world. Okay, so with that, let's try to understand different case studies. So let me discuss first of my case study. Okay, now this is what is talking in sense like what work I have done during my PhD at IIT Bombay. Okay, so I acknowledge that part. Let me move. Here, if you look at, this is what we were discussing. Now, what it says, in order to have your high thrust, you can say you increase the diameter of your, you know, your disc fan. That's what we are doing. Suppose say I'm increasing the diameter. What will happen? Your engine that you are putting below your wing, it may be possible that the larger diameter, you will not be having sufficient ground clearance. Let me tell you, larger diameter in the sense, at this moment, the maximum diameter, that's what is say 2 meters. So it's not a small diameter. Now, when you are takeoff or landing, there may be chances that this engine will touch to the ground. And you can understand, if it is touching with the ground, that's what is creating a whole lot of trouble. Okay, now you need to go for testing of all engine. You need to go structural testing for your aircraft. You can understand that's what is very time consuming and very expensive affair. Okay, so what people say, like we are having stage, say here if you look at say rotor and stator kind of combination, it says like in place of having this rotor and stator combination, let's think in sense like having something different. Now here what people they understand is rotor, it's a rotating device, and stator, that's what is a stationary device. So general understanding for those who are not having background of aerodynamics for compressor, they say, or maybe in many literature or in open book, it says stator, it is to guide the flow only. With that understanding, what they say, like if it is guiding the flow only, then let's try to remove this stators. If we are removing this stator, what will happen? It says it will be reducing overall weight of my engine. And if I am reducing overall weight of my engine, I can say I can reduce the drag of my aircraft. And if that drag is reducing, it says I can improve my fuel economy. Now that's what is a requirement these days. You can understand, say, rising price of your aviation fuel or petrol or diesel every day, that's what is giving you green signal or red signal. You know, for many it gives, say, red signal. For researchers like me or like the group of people, you know, for them it's a green signal. Now I say yes, when this price is rising, you know, like now the research, that's what will be coming into the picture. People say you just give the solution for this kind of troubles, and that's what is putting in terms of number of projects. Okay, and that's what is giving us bread and butter. Just joking. Yeah. Okay, so now here in this case, people, they started thinking of having, say, contra-rotating kind of configuration. So here if you look at, this is what is one of the rotor, that's what is rotating in clockwise direction. Other rotor that will be rotating in anti-clockwise direction. So what it does, it says we are removing the stator. Now this concept, it seems to me, you know, like little odd in sense, but this is what is not the recent or new concept. This all are the existing engines which are available at this moment. This is what is a Russian engine. That's what I say, unducted contra-rotating fan. Here if you look at, this is what is, say, GE engine. That's what they have developed during 80s. Okay, that time the price for the crude was so high, and that's the reason they have found this to be one of the alternative solution. In 81, now that price gone down. That maybe you may be aware of Kharagpur. So during that time, the people, they started working. Now price fell down, and that's the reason they stopped working on this project. Now again this price is moving up. So many of my friends in US, they people, they are working at this moment on this engine. Okay. Now the thing is, you know, in terms of certification, they are facing difficulty. Why? Because you can understand, when you are sitting beside your window in aircraft, you know, these rotors, they are rotating opposite direction. That's what is scary. And you know, like maybe for Indians, it's not that challenging or it's not that risky, but for, say, foreign, mainly say US people, they are very scary and they are not giving the certification to this kind of engines. Okay. Now here if you look at, this is what is a fighter engine. That's what I say, F-135. So that is called 5th generation aircraft, in which you will be having, or you are having at this moment, all your rotors are contra-rotating for compressor, all your stator for the rotors for the say turbine, they are contra-rotating. This is what is one of the project, that's what is being run at, say, Europe, like group of different universities and companies. They are working with 3-spool configuration. You can say this is what is, say, my high speed spool. That's what is, say, it is rotating in conventional direction. But here if you look at, in place of having, say, LP, they are having contra-rotating fan. Now you just try to understand the benefit here. You know, they have reduced the number of stages required in sense of LP turbine. At the same time, they have reduced the diameter of this, you know, fans by using contra-rotating concept. Okay. Now, in line to that, like, let me say, like, just try to understand, this is what is your conventional stator-rotor combination. I can say this is what is at midsection. Just try to understand me. If I'll be putting this number of lines, you know, this all lines, that's what is showing all aerofoils. Okay, let me tell you, this peripheral speed U, it is nothing but it's a function of, say, my diameter. So here if you look at, here in this case, at this station, I'm calculating my U. If I'll be putting this at, say, tip here, so my U, that's what is changing. So my angles, you know, like beta 1, beta 2, alpha 2, alpha 3, they all are getting changed. And that's what is giving me, say, 3-dimensional shape. Okay. Now here if you look at, this is what is with the contra-rotation part. you can look at, this is what is the rotational direction for my rotor 1. Now, you know, like if you compare here, this is what is a whirl component, that's what is coming out from my rotor. And what we are doing, we are, you know, we are straightening the flow, we are trying to remove this whirl. Okay, in the case of contour rotating, what we are doing, we are rotating our wheel in opposite direction so that my CW2 direction and my U direction, that will be same. So that's what is giving me high relative velocity at the entry of my rotor 2. And this is what is the exit of my rotor 2. Now, what all are the advantages? As we have discussed, we will not be having any stator vanes. That's what is reducing my size and overall weight of the engine. It says we can extract more amount of work per unit length. That's what we have seen for F-35. High relative velocity, so there is no need to rotate the wheel at very high speed. That's what is the benefit. If that's what is the case, you will be having lower centrifugal stresses. It says there is a significant improvement in aerodynamic performance as well as efficiency. And it says we are reducing the size, weight, number of components. That's what is reducing the manufacturing and maintenance cost. Now, these all are the recent ongoing activities on your contour rotating concept. Now, let me tell you, this is what is the work I have done in terms of design for contour rotating fan. So I was having, say, bell mount, that's what is having, say, diameter of 406. So that's the reason I have fixed that. I was having my motor, that's what is rotating at 2400 RPM. And this is what is the power requirement. So that's what is used to decide, you know, like this is what you need to understand. Say, this is what is used to decide the different parameters. So for my first rotor, I was having my pressure rise of 1100 Pascal. For the second rotor, I was expecting my pressure rise to be 900 Pascal. Okay, and you know this aspect ratio, what we are talking of, that's nothing but the height of the blade to chord. That's what was small. Say in sense, it's a big one. So you can say this is what is in line to what we are having in terms of fan. So let me show you here. I'm talking about this fan. So you can say this is what I'm talking of. So it is in line to this kind of concept. Now, these are the design steps what we have followed. So it is based, you can say, some of the parameters which I was already having. Based on that, we have selected our geometrical parameters. Then based on our velocity triangle, we have calculated our angle, various velocity components. Then these are the aerodynamic parameters. When you are going for design, you need to have check on I with diffusion factor, degree of reaction, power requirement, all those terminologies. Then we are having, say, loading of my my total loading on the blade. That's what along the span, how it is varying. Then after we have done the calculation for different angles, we were having, say, stacking of the blade. I will show you all these things. Then after we were having, say, check computationally whether it is giving the expected results or not. If not, then we have done modification in terms of changing number of blades, aerodynamic loading, flow angles, custom tailored aerofoil, and in order to meet the requirement. So whole purpose for doing this computational study, let me tell you, that's what is for the development of experimental facility. Those who are interested, maybe can download the paper. That's what is available on ResearchGate. Let me show you. So these are my two rotors. Okay, here if you look at, I was having 19 and 17 number of blades. So I have one domain of rotor 1, second domain. These two domains, they are being put on, say, interface. I'm having my inlet boundary condition. You can understand, suppose if I say 19 and 17 number of blades. So if I'll be making my full domain or full rotor, then it requires a whole lot of computational power. Okay, at the same time, what software we are putting or using, that also has constraints in terms of, say, number of elements, because you know it's a university research. Okay, so that's the reason why what we are doing is we have selected one blade for both. Okay, and here if you look at, we have taken this and other side, that's what is as a periodic boundary condition. So here this is what is my periodic boundary condition. Here this is what is a periodic boundary condition. Periodic in the sense, we can say it can easily exchange the data, like the way in which the number of blades they are being arranged. Okay, so these are the mesh qualities. As I was saying, initially I was having this kind of aerofoil. That's what is my original aerofoil, both for rotor 1 and rotor 2. Based on computational study, as I was saying, I was able to receive or able to achieve what pressure rise I was expecting, because my target was to achieve pressure rise with maximum efficiency. So this is what is modified aerofoil. Now, like if I say big giants, say maybe GE or Pratt & Whitney or Rolls-Royce, all these people, they are having, say, research activity. That's what is going on, and they are making those all works as a proprietary nature work, and they are registering the patents. So yearly, as per the data, for GE, they are registering 3,000 patents a year. Out of that, almost 2,000 patents are only for the development of aerofoil. And that's what they are saying in sense like export control or quality control. And that's what is not they are putting in any open domain. So it is very difficult to get this kind of aerofoils in open domain. Okay, so this is what is original SIPO profile. Now I have modified. You can understand what exactly I have done. I have modified my maximum thickness. I have modified the location of my maximum thickness, putting all angles same for both the aerofoils. Now these are the geometrical parameters. Now this is what is my experimental facility. Let me show you here. This is what is experimental facility. That's what has been developed at IIT Bombay. So here, if you look at, this is what is my case section, in which I am having two rotors. So this is my rotor 1 and rotor 2. So my study, it was focusing on various aspects. One of the aspect is like it was like what need to be the minimum distance between two rotors. So you can say I was using the spacer here. So in between I was putting my spacer. So here if you look at this particular section, that's what is fixed. So my front rotor, it has been rotated by this shaft, and here downside I was having my one motor. For rear rotor, I was having motor here on the rear side. Okay, since I cannot move this part, I was having provision to change the axial spacing. Okay, and based on that, I was doing my experimentation in order to check what need to be the minimum spacing between these two, which will be giving the best performance. What is the effect of rotational speed of these two rotors? That's what is the second target. Third target, that's what is how my two rotors that will be behaving under distorted condition. Okay, so like the use of this CFD, what I was saying, that's what is being used in order to develop these two rotors. Okay, now like these are the measuring instruments. These probes, what you are looking at, they are called kill probe. They are also being developed based on the results what we have achieved from CFD analysis. Okay, so these are the kill probes. This is what is called, say, your say pitode tube or pitode kind of probe. That's what is placed in the inlet. At the exit, you will be having flow angularity. So by providing this kind of chamber, it will give the smooth entry to the flow, and it will give exact measurement of my pressure. So this is what is the effect of change of axial spacing. Okay, so conventionally, if you are looking at, so this is what is a performance map for conventional low speed axial flow compressor. What you can say, like by decreasing your mass flow rate, your pressure that will be rising. After some point, there is no further rise of pressure. That's what is possible. That's what is called, say, stall. This is what is a stall condition. Here, if you look at, say, what we were trying to explore, so if you try to understand, this is what is showing three different speed combination. In sense, by rotational speed for both rotor, there were, say, 2400 RPM. In this case, it has been increased by 8%, 2600 RPM. Here, this is what is 2200 RPM with different axial spacings. So you can understand how my change of speed, that's what is affecting. And here, very interesting to observe, your performance map, you are having peak value here. That's what is called, say, mild surge region. Okay, so you will be having, say, mild stall, or we can say this is what is the region where your second rotor is getting stalled, and this is the region where my whole stage, both the rotors are getting stalled. Let me tell you what is the meaning of that. So here, if you look at, this is what is a performance map for my rotor 1. If you try to understand, this is what is my efficiency, and here if you look at, these are my pressure values. So for my rotor 1, over a wide range of my mass flow rate, it is not getting stalled. So for all speed combination, if you look at, my rotor 1 is not getting stalled, while for second rotor, if you look at, this is what is behaving like your conventional rotor. What it says, like after some point, that's what is getting stalled for different speed combinations. Now this is what is like we have done in terms of, say, experimentation. Now let me come back again. Say, like, we have used our computational tool for the development of rotors. That's what is for one design condition. Now when we are doing our experimentation, that's what is giving me this kind of performance map. When we are doing our experimental study, you know, because my second rotor, that's what is getting stalled, so I am unable to do prediction on this particular region. So I can predict only by first stall or mild stall. I cannot predict this particular region for all the speed combination. And there is discrepancy when I am talking in terms of high mass flow rate region. Okay, then people always will say, like, you know, like what you have designed, is it giving you what you are expecting? So this is what is a validation. So this is what is for, say, my design mass flow rate. Here, if you look at this line, say black lines, that's what is showing me, say, experimental result. And here, if you look at, these are my CFD results. Let me tell you, like this CFD analysis, that's what has been done by experimental results. So at the entry, as I was showing, we were having, say, pitot tube rack. That's what was giving me total pressure. So that total pressure we have used is an inlet boundary condition here. Outlet boundary condition we have taken as mass flow rate. And that's what is giving me this kind of comparison. So if you look at, for design mass flow rate, we are having some discrepancy, but you can say there is always measurement uncertainty. That's what is present in experimentation. So you can say it is valid well. Here also, if you look at for, say, your rotor 2, that's what is working fine. It's giving good matching, except near the tip region. This is what is, you know, like CFD is unable to capture in sense of measurement for contra-rotating case. So here, this is what is for peak pressure mass flow rate. It is, you know, it is giving very good comparison between these two, experimental result as well as the numerical result. So what I want to convey is, you know, like you use your tool. That's what I say as colorful display or CFD tool. So for all this work, I was using, say, ANSYS CFX as a tool. Then after, you know, after development or after doing your analysis, after doing all your design iterations, why I have done all design iteration? Because I want to reduce the manufacturing cost. I want to reduce the cost of making of these two rotors. That's what is possible by using this CFD tool. So it gives quick in sense of solution. Otherwise, I need to make number of rotors. After that, I need to find the best one, and then after I will be moving ahead. So that's what is saving our time and our efforts. And you can do now here, if you look at, that's what is giving again recheck in sense of how your design it is been validated with. Okay. Now let me tell you, like this is what was, say, my first case study and building of confidence using CFD tool for the development of experimental facility. Okay, let me show you here. This is what is, say, my case study. This is what at IIT Kharagpur. So here, if you look at, as I was saying, you know, like in order to increase your pressure ratio, you need to increase your temperature ratio, and that temperature ratio, it is related with your delta beta. Delta beta is nothing but the turning of this plate. Now suppose, say, I'll be having higher delta beta, as I was saying, there are more chances for my flow to get separated. And if it is getting separated, you can understand that's what is reducing my operating range or your whole compressor stage that will go in stall or surge. Now, like people, they are finding the way in order to address this issue. What is the reason? Because you can say, if I'll be putting larger delta beta, means higher compression ratio I'll be getting per stage, then it will be reducing your number of stages. And in order to address that, people, they are using this kind of tandem configuration. So here, if you look at these two aerofoils, they are being placed in tandem arrangement. So what will happen? You will be having one wake that will be coming out here. Now, because of jet effect, that's what is flow coming out from your pressure surface, and the acceleration of flow from your suction surface, that's what is reducing the separated flow region, and that's what is giving you small wake. And this is what is giving you the indication for future compressors, and that's what we have taken as a challenge. Here, if you look at, these are the two stages which are being designed. Suppose say I want to reduce the length of my stage, I can incorporate the tandem stage. It says if you will be having this tandem rotor kind of configuration, you can save 30% of your length of the engine. Let me tell you, like, we are reducing the number of stages, that is one thing. Secondly, we are reducing the overall length of the engine. Now let me tell you, when we are decreasing the length of the engine or maybe length, then like your shaft on which you will be putting this rotor, those shaft length also will be reduced. Now there is a particular weight for that shaft. Okay, so the weight of that shaft also is reducing. So you can understand, in overall sense, we are trying to achieve overall reduction in weight, overall reduction in length. And that's what is the promising part. So here, if you look at, this is what is a work, that's what has been done by one of my PhD students. This is what is ongoing activity. So these are some of the range, that's what is being placed. Okay, we are working in this particular range. Okay, we are having this as our design tracker. Now, in order to have that kind of configuration, I say this as 4-blade and half-blade kind of configuration. Now here you need to understand, suppose say I'm putting two separate blades, then I'll be having the discontinuity in the flow. So the shape of my blade, that will be different. Now if you try to understand, say this is what is my casing. So in casing, if I'll be using this kind of configuration, it may be possible that I'll be having great tip clearance. That's what is possible here. So in order to maintain that constant tip clearance, we are having this kind of shape. Now there are two possibilities to be addressed here. One, that's what is called say percentage pitch, and second, that's what is called say axial overlap. Let's try to understand what is that. So for all our studies, we have kept percentage pitch to be 82%. So you can say percentage pitch in the sense, like what is the gap between these two rotors in pitch-wise direction. Okay, that's what we have maintained constant. Then we have varied our axial overlap. Now let me tell you what is the reason here. So here, this is what is showing in sense of your conventional cascade plate. Okay, so many people, they are doing their experimental work. Many people, they are doing work for cascades. Okay, when we are talking about real rotor design, that's what is all the way different. And that's the reason here, if you look at this axial overlap, what we are having, that's what is different. So we have studied say 0, -5, 5, and 3%. You can understand we are using our computational tool in order to do the iterations for change of axial overlap with different kind of configuration you can see here. Now this is what is with say 0 axial overlap. So you can understand this trailing edge of my fore say rotor and my aft rotor. If you look at here, that's what is say 0. So if you try to understand what is happening in this particular region for say my 4-blade configuration, so color code I maintain in that sense only. So for my 4-blade configuration, if you look at, we are having great separation. That's what is happening around in this region, say maybe 85% of span. This is what is at say 85% of span. Now what is happening? We are taking or we are getting the benefit of acceleration of flow because of this nozzle effect. So you can say there are less chances for my flow to get separated from this surface. Okay, but in overall, if you look at, you will be having my separated flow. So how this separated flow is coming? You can say the separation, that's what is happening on my suction surface, and I'll be having jumping of flow because of tip clearance. So here we have maintained the tip clearance of 3 mm. So you can understand large tip leakage flow, that's what is coming out, it is getting rolling up here. Now in order to address that, we tried with say -5 overlap. So you can say here in this particular region we are moving far by say -5 degree of -5%. So here in this region you can say I'm having more chances of my flow to get separated from this blade. Okay, this rear blade, that's what is getting separated. From my front blade also I'm having flow separation. This all together, that's what is giving large flow separation. Now you just try to understand the meaning of flow separation in the sense, like this is what is unavoidable, because that's what is going to happen because of presence of your tip clearance. So we need to minimize the extent of this loss. Okay, this is nothing but it's counted as a loss. So that will not, this particular region, that will not give rise what pressure rise we are expecting. Okay, then we have explored with say 5%. You can see now you have your clean flow, that's what is happening for your rear blade. No doubt on the front blade you are having great acceleration, that's what is giving me lesser span in that sense. Then this iteration that was continued up to say +3% axial overlap. So this is what is my final part, and you can understand the flow behavior in sense what is happening. Say my extent, that's what is changing with changing of axial overlap. Now just try to understand, say this is what is my rotor, and I'll be having low momentum fluid, that's what is coming out. What is that low momentum? This is what is low momentum fluid. As I say, now what will happen, this low momentum fluid that will be striking on my stator. So here you can say this is what is showing in terms of entropy, we can say it's a loss. So that will be striking here. So like what pen paper calculation what we are doing in sense of design, okay, that we will not get when we are having this kind of configuration. Now let me tell you, until and unless you are having your tool in order to capture, in order to understand, it will be very difficult to understand this phenomena. You can say before 80s, like people, they were doing all kind of experimentation, whole lot of experimentation they were doing in order to understand that part. Now using your computational tool, it is possible to reduce those number of iterations. Now like this is what is happening. Now in order to address this, what stator, say this is what is originally been designed stator. Then later on we realized this stator will not help. I will show you the results. That's what is not helping in sense of addressing. So we were having great flow separation or the stalling of stator. That's the reason we have modified. So this is what is called orthodox design. In sense, you just look at the stator blade, it is 3-dimensional in shape. It's having this kind of distribution of angle. That's what is called dihedral. Okay. Now, like once we are doing this study, like try to understand this is what are the angles. These are the design angles for my front rotor and the rear rotor, and this is what we have achieved with the say CFD study. So here, if you try to understand, my physics, that's what is different. It is not following particular pattern. Say it is matching well for up to 60% for the front blade, and then it is matching near to above this 80% span. And that's what is because of what wakes that will be coming out from my rotors. So in order to address this issue, we have taken out the average angle. Okay, and you can see in this particular region, like this is what is a region where my blade, it is working fine in sense of it is meeting with my angles. But on above side, I'm taking the benefit of your jet effect, but at the same time, it is spoiling my flow behavior in this particular region. Okay. Now, this is what is we are achieving. You can understand this is what is my conventional stator design, in which I was having, say, stalling of that stator. This is what is a design condition. Then later on, we have modified that part, and you can see this is what is. So, like to put those losses to be zero, that's what is next to impossible. But at the same time, we need to understand we are able to minimize these losses. Now, suppose say you are doing your iteration without any use of computational tool, you will never reach to what you are expecting. That's what I want to convey here. Okay, so this is what is my separated flow region isosurface. This is what is in terms of, you will be having combined effects. Okay. Now, based on that, this is what is the experimental facility. That's what we are developing. Okay, so these are the final rotor blades, final stator blade. You can see this is what is a combination. This facility, that's what is a unique facility as on now at India, especially when we are talking about the tender rotor kind of configuration. But later on, we can use this for many other applications also. Maybe if I want to test different kinds of fans, I can do that testing. Okay, now here if you look at, this is what is called entry of my flow. That's what is my bell mount. If you look at my earlier slide, what I was saying at IIT Bombay, that's what was having larger size of bell mount. That larger size bell mount, it was made from wood and it was older one. Now here, since I need to develop at my own, so I need to design this particular, say, intake part. So let me show you that part. So, like this is what is the work, that's what was done by undergraduate students at Nirma University when I was at Nirma University as associate professor. Now, my target, it is to minimize the size of this bell mount, because if I'll be having larger size, the cost for making that will be increased. At the same time, if you look at, there need to be certain amount of clearance between ground and your intake. If I'll be having larger this bell mount size, then my height of the setup will be increasing. So that's what is a constraint to me. And in order to address that, we have used three-circle method, we have used, say, aerofoil section, then we have used elliptical method. So here, if you look at, this is what is my flow behavior. So, by using this three-circle method, that's what was giving the large variation of my, the dimension. In order to address this, this is what is a final dimension. Let me show you. This is what is the experimental facility. That's what has been developed. Now it is, maybe by next month, it will be under working condition, because these rotors and stators, they are under, say, fabrication. So you can see this is what is a bell mount, what I was talking of. So now, like you can have your quick check in terms of designing, say looking to picture or looking to geometry. If you will try to make, I'm 100% sure you will not get what you are expecting. Be careful. You need to be very handy with the number of tools available with you. Gone are the days where you are not having the resources. Now you're having all kind of resources, so utilize those resources. Okay. So this is what is the second facility, what I was talking in terms of, say, low speed axial flow compressor testing. Okay. Now let me discuss with my, say, case study 3. I'm sure I'm having 20 more minutes. Yeah, Professor Maharshi.
Yes, sir. We are having 20 minutes.
Fine. So let me show you. This is what is called Cascade. So before your arrival of CFD, let me tell you, people, they are claiming so many things, but basically the invention for CFD, it was initially been done for turbo machines application. Let anyone to say anything, you just go through the background, you just go through the literature, you will understand, like in order to minimize the number of efforts, the cost, everything, people, they were putting a whole lot of efforts for development of computational tools. So in 80s, we were able to have that kind of codes. Okay, Before that, what people they were doing, they were testing the blade sections. So here, if you look at, this is what is my rotor and stator combination. It may be compressor, it may be say your turbine. So at mid section, as I was saying, I can have my angles. So at this section, I can have my aerofoil. Maybe if I'm moving upside or maybe I'm moving say downside, you can say the shape of my aerofoil that will be changing. So what they were doing the testing using the cascade facility. Okay, let me show you those cascade facilities. So here, if you look at, say this is what is your actual blade. So if you try to understand at different sections, you are having different angles. So that's the reason why what they are doing. They were doing testing at say hub region, maybe they are testing for say mid section, maybe they were doing testing for tip section, and based on those all experimental data, so you can understand NASA those days they were working hard in order to generate all this data, and those data they were transferred to say engine manufacturing companies. So they were together, they were working. Okay, so a whole lot of database, that's what is available in open domain, which is not in use at this moment to them, and that's the reason why it is available in open domain. But we can use those data for our understanding. Now, in order to do that testing, we are having different kind of possibility. So here, if you look at what I was saying, so this is what is one of my section. So that section they are arranging, so hold the span, it is having same shape as this aerofoil. Just try to understand that part. I forgot to bring the linear cascade I was having, but you can understand this part. So this is what is a linear cascade. They are being arranged in a linear way. So this is what is called linear cascade arrangement. Now, like this is what is doing testing for one particular section. So for different sections, you need to have number of tests. Again, you will be having number of blades you need to fabricate. So that's what was increasing the cost and number of hours, and then after analyzing the result. But still, people as on today also, they are working on linear cascade in order to understand the flow physics. So in order to avoid that kind of situation, people, they come up with say annular cascade. So you can put your actual blades. That's what is having all variation of angle. And that is also is in use. But you can understand, suppose if I say I want to test my compressor rotor for say HP, you can understand I want high pressure rise at the entry. At the exit, I will be getting high pressure rise. But in order to achieve that high pressure rise, you need big size of blower or maybe compressor itself. So that's what is increasing the cost of testing. Okay, so here let me show you. This is what is a linear cascade tunnel. That's what is available at IIT Kharagpur. It was been designed by Professor Bhaskar Roy, who was ex-professor at IIT Bombay. He was earlier faculty here. Now this, it has been modified by our group. Now we have changed our test section. So you can see this is what is the test section, what we have developed for the testing of blades. Okay, so this is also one of the ongoing work at IIT Kharagpur. This is what you can see. You just look at, this is what is NTUA linear cascade facility. If you try to understand, this is what is their well mount. They are having compressor testing facility. Then they are having say wind tunnel testing facility, and then they are having this linear cascade. So they are utilizing whatever space is available with them. I'll be discussing this part when I'll be talking about my own case. This is what is cascade tunnel. That's what is available at NAL Bangalore. That's what is say transonic kind of testing. It's a blowdown, so you can do the testing for Mach number up to 1.5. What this you are looking at, that's what is say subsonic. I can go with maximum velocity of 50 meters per second. But it depends what kind of experimentation are you doing. Now, like this is what is say other kind of facility, what people they are talking of. That's what is called say sector annular cascade tunnel. Now, as I was saying, when you are doing your testing for say compressor or turbine as whole stage, you need to make all lot of blades. Your power requirement, okay, your mass flow rate requirement, all those things, they are very expensive affairs. So in order to avoid that kind of situation, rather having all number of blades, we can use few number of blades, and we can do the simulation as like in actual condition. So this is what is a facility, that's what we have developed here. This is what is a first time in India. It's a unique facility. That's what has been developed at IIT Kharagpur. So I'll be talking about the use of CFD for this time. Let me go here. So this is what you can see. So this is what is like based on our expected Mach number of 0.64 at the exit of my nozzle. We have done our calculation in terms of what mass flow rate is required and what pressure rise what we are looking for from the blower. Now based on those lower dimensions, you can say if I'll be accommodating my, this is what is my sector annular cascade tunnel. So that's what is showing me here. If you look at, because this height from ground layer it is higher, I'm having very high level of test. So my test section, that's what is coming at high level. Second constraint with me is in available space at our lab. You know, I cannot move beyond this height. So if I'll be using this kind of design configuration, okay, then I cannot fit this tunnel in my available space. So now just try to understand what I'm discussing here. Say this is what initially we have been designed, but later on with available blowers in the market, and you know, like the purchase policy is such, like you need to purchase your blower. Based on that blower, you need to think of all this calculation because of, you know, tendering process and all those things. Many of you may be aware of, maybe few of you may not be aware of, but that's what is the policy by government of India in terms of procurement. So once we got the idea about the size of the blower, it says like we need to do something in terms of design. So here if you look at, this is what I was saying in terms of my constraint. Okay, so this is what was my initial design where my blower was not of this size. Now since my blower size it was fixed, and as I say, like I need to have the constraint in terms of height of my test section and the available height, I need to modify my design. So here if you look at, this is what is a modification of my design. Here if you look at, I'm having, so here if you look at, this is what is say parallel wall kind of configuration, but it is inclined at some angle. Here this is what is my diffuser. Okay, that diffuser I need to modify like this. And then after that, I need to have my transition section in order to have the linear exit. Let me tell you, like, you know, like your blower, that's what is giving particular mass flow rate. Now, in order to accommodate that mass flow rate, you need to have larger size of your flow. Okay, here, this is what is my diffuser section. You can understand this diffuser section, basically what we are doing is our kinetic energy we are diffusing here. That means we are raising our pressure in this particular region. Then after what happens, I need to have my flow to be with uniformity, and that's the reason here if you look at this particular section, that's what is called my, you know, like honeycomb section. I'm having 3 different screens. I will show you this part. Then after here if you look at, this is what is modified of my shape. This modification of shape, that's what is also being done using CFD, and this is what is. Okay, let me show you this part. So this is what we have done in terms of our computation. So just try to understand, say I'm having my inlet, that is nothing but the exhaust, that's what is coming out from my blower. That's what is available in terms of my diameter and in terms of mass flow rate, so we can have inlet velocity at the entry. Now this is what is my diffuser, say connecting section. I have my honeycomb section, I'm having my screens, I'm having my exhaust. And here if you look at, this is what is my nozzle. Now listen me carefully. When people, they are doing their CFD analysis, many things they are not considering, they are taking everything granted. If suppose if this work is assigned to somebody who is doing BTech or MTech, what he will do, this is what is my inlet condition, and exhaust will be, he will be saying, say, outlet condition. But you need to understand what exhaust that will be coming out, that will be going to open domain or in open atmosphere. So this is what we have simulated using this spherical shape. That's what is called opening boundary condition. Okay, so let me show you. Now just try to understand, suppose if I'm talking about, say, the diffuser, the toughest part in engineering design, let it be mechanical or let it be, say, aerodynamic, very challenging part in terms of fluid mechanics of aerodynamics, that's what is to design the diffuser. Okay, suppose if I consider this is what is my diffuser, if it is a rectangular one, it will be having, say, W1. If it is a circular one, it will be having, say, R1. This is what is my entry, this is what is my exit, and I'm having, say, my angle. Say this is what is my diffusion angle, this is my overall length. So what we are expecting in terms of our flow, we, like this is what is acting under adverse pressure gradient. So my entry pressure is lower, my exhaust pressure is higher. That means there are more chances for my flow to get separated from this one. Okay, here if you look at, this is what is the case. What it says, this is what is, say, my entry, this is what is my velocity. Here if you look at, this is what is giving me the separation of my flow. What is the reason? Because any change of parameters, suppose, say, my length I am changing, my angle will be changing. There are certain range beyond which you can move. You cannot increase the diffuser angle. Now I was having constraints in terms of overall length available in order to accommodate the tunnel. So you can say this is what is my constraint. So let me go here. Say here if you look at this total length available in my lab, that's what is my constraint. So you can say in order to avoid the separation of your flow, you can make say larger length, but that's what is not possible for me. Okay, so now in order to avoid that kind of situation, anyway forcefully it is giving larger angle here. So that's what is being addressed by incorporating the screen. Screen in the sense like it's a porous material. You can say like what we are using for, say, for your compound kind of thing where you are not permitting something to enter kind of thing, what we have incorporated here. So this is what is my screen. And here if you look at the address for the separation, it is being handled here by using this screen. Now in order to simulate this screen, we cannot make the screen that's what is having, say, dimension of, say, 1 mm gap and having, say 1 mm diameter. So if I'll be making that kind of solid model, it will be very difficult for me to do the massing. So there is a special provision that's what is available in ANSYS. They are saying porous media. So you need to define your porosity and permeability. So that's what is being used here. Now for our case, what we have done, since my angle is wider angle, and since I have put that inclination, so we need to incorporate. So here if you look at, we have kept our screen here, and that's what is trying to avoid the separation kind of situation. That's what is happening. Here you can see what color code it says. It is not 0. Just try to understand that part. So I'm having that velocity to be higher. So you can say like you can use this tool in order to have this kind of design. Now this is what is my Mach number. As I was saying, at the exit of my nozzle, I was expecting my Mach number in the range of 0.64. So here if you look at the entry of my diffuser, I have relatively clean flow. Now when it is moving downside, I'll be having the growth of boundary layer, but my core flow, that's what is same as what I'm expecting. Now when we are moving downside near the exit of the diffuser, you can say because of large angle, you will be having this kind of situation. So I'll be having my low momentum fluid, that's what will be present, but my core flow region, that's what is remain as it is. Now by using this honeycomb section, if you look at, we are able to achieve the uniform velocity at the exit. Further, it has been unified by using, say, the screen 1, 2, and 3. That's what is having porosity of 0.6. So last screen what we are having. So you may be aware of the wind tunnel. So that's why I'm not addressing this point. But you need to understand Here what flow, that's what is entering, that's what is having large angularity. So you will be having bigger wakes, that's what is entering inside. Now what this setting, this honeycomb section, it does, like it will be converting those big size of wakes into smaller size of wakes. Okay, then again that will be passing through these screens, so that will be reducing my AD size, and that's what will be giving me uniform flow here. Okay, and here if you look at this particular location, I'm having this kind of flow distribution. Okay, this is what is at the entry of nozzle. Now this nozzle, it is also been designed by using say 9th order Coulomb wave. Maybe I will show you that part. Now this is what is with different inlet velocity. You can understand I may need to check my cascade at different flow velocity, different Reynolds number, different Mach number. So I need to vary my inlet mass flow rate condition. So here if you look at with changing say maybe from 40 to 24 meter per second, the core region, that's what is not getting affected at the entry, and at the exit also here if you look at, I'm getting kind of uniform flow. Okay, now this is what is that sector annular cascade tunnel, that's what is ready with. And here if you look at, this is my blower, what I was saying in terms of space constraint, you can understand this part. This is what is my nozzle, and this nozzle, this is what is my exhaust. Okay, now this exhaust I am able to achieve like the speed of, let me show you, like this is what we have commissioned yesterday only. I was very much busy with all this testing and commissioning part. Let me show you this testing. So this is what is my suction, and here if you look at, so at the exit of my nozzle, I was able to get uniform flow. Okay, that's what is my expectation. Okay, so you can say this is what is one of the use of your tool in terms of development of experimental facility. That's what is not possible with your thumb roots. Now, at this moment, this facility we will be using for testing of the turbine vanes. So here if you look at, this is what is the number of stages for E3 engine. That's what is when given by Pratt & Whitney. As I was saying, like no details you will be getting in open domain. Luckily, we have few details available with us, and that's the reason why we have selected this. So it says near the hub for third stage of nozzle vane, they have given the CP distribution. Okay, and based on that, we have developed our own blade. So you can see this is what is the CP distribution. That's what is meeting well. Now, you know, the shape of my leading gauge and shape of my trailing gauge, that's what is a proprietary kind of nature. And that's the reason why that data or those data, they are not available openly. Based on our iterations, number of iterations, we are able to achieve the flow acceleration and deceleration on leading edge and on trailing edge. So you will be having some discrepancy here in sense of the available, but that's what is within the range, maybe plus or minus 2%. So that's what is accepted. Now here, like as I was saying, like this is what is our tunnel, and now we need to do the testing of my blade. So this tunnel is ready with next component, that's what is to make the test section. Okay, so this is what is my test section. Now that test section that will be connected with the diffuser, because you can understand, say I'm having number of blades that this particular vane, they are having say 72 number of blades. In place of 72, sorry, I'll be using 9 blades. So this work is in progress. Initially, we have started with this kind of diffuser section with test section available here. But later on, we realized we are not getting what we are expecting in terms of actual engine condition. So that's the reason we are putting our flow controllers. This work is in progress. Now, with your due time, this is also one of the work that's what is going on at IIT Kharagpur. So we are making closed tunnel. Okay, I'm a group member for this ongoing research work, which will be used for high-speed train testing or railway engine testing. Okay, so this is what is a closed circuit wind tunnel, what we have designed using CFD. So maybe someday, if time permits, we can discuss. So you can see, like, this is what is a huge tunnel. Okay, let me tell you the dimension. In sense, this diameter what you are observing for this fan, it is 4 meter. So you can imagine the size of this tunnel. Okay, so that testing or that kind of design we have done using this CFD tool. Okay, so let me come to the point. What all we have discussed? We have discussed about, say, actual engine testing. Then after we have narrowed down in terms of, say, experimental study or rig development, why we are going with low speed testing. We have discussed about various design aspects, design modifications, interpretation of your computational results, and experimental setup development. Okay, so these are some of the activities which is highlighted with blue. That's what is going on at IIT Kharagpur. This is what you can say, that's what is going on globally. So this is what is particular region for the research where we are lacking. Okay, if you look at in terms of development of engine, we are not able at this moment. We are also sort of, say, manpower, those who are having, say, expertise in this particular domains. Once you will be in this domain, you will enjoy, you will do your work, you can do ample of things. Okay, let me finally conclude. Thank you very much. Like, if you have any question and answer, say maybe interaction, if you are looking for, I'm open to discuss. Thank you very much for your patience.
Thank you. Thank you very much, sir. Any participant having any question, they can ask. Yes, any participant having any question?
Hello.
Yes.
Good afternoon, sir.
Yeah.
Sir, I have heard that every engine main technology is core technology. So, what is the core technology for any engine, which is a very crucial part of engine technology? Core technology.
So you need to interpret in sense, like, suppose if I'm saying, say, you are working with one of the companies, say GE, I'm working with, say, other companies, say Rolls-Royce. Now, you know, airline companies, say maybe Boeing or maybe Airbus, they are looking for the engines. Now, when we are talking about these engines, you know, you need to beat, you need to compete with your competitors. Now you are claiming, say, my engine, that's what is generating this much amount of thrust, and this is what is fuel economic, and overall efficiency of my engine is this much. Now, few point improvement here and there. Let me tell you, say, compressor as on now, that's what is reached to, say, maximum efficiency of 92%. Okay, now in numbers, when you are talking to mechanical engineers, they will say you're just bluffing, but yes, we are able to achieve this efficiency now. So, you know, small improvement in your efficiency for one of the stage for compressor, that will give you big impact in overall costing. Say, when I say annually, if I'll be measuring or calculating my fuel economy, you will understand it's a saving of billions of dollars. So that's what is called core technology. That's what is not being said in open domain.
Okay, thank you, sir.
Yeah.
And sir, one more question. Sir, recently I have heard that our DRDO and Rolls-Royce will working on the development of whole new engine for our future aircraft, future military aircrafts. So it is why we are collaborating with Rolls-Royce. It is not possible in India for us to develop our indigenous aircraft.
You know,
Aircraft
like,
engine. We have developed Kaveri engine, but it is not that much thrust is not that much high what we want.
so you can understand what is the importance of trust. If you are not achieving that trust, it is of no use. So, you know, like, you need to have field experts. So what I was talking to you or what I am talking at this moment, that's what is mainly on aerodynamics. There are many aspects, other aspects also, thermodynamics, heat transfer, material. Okay, then you are having, say, maybe in sense of, say, vibrations, you may be having rotodynamic part. So all those things, it required specialization, and that specialization required a whole lot of efforts. That's what we are doing. Okay, so if you look at, say, all universities, if you count, very few universities, IITs or NITs, they are having specialized course. They are talking in terms of, say, turbo machinery. I say in overall. Now, if you try to Google maybe on, say, maybe in Europe or maybe in US or maybe in Germany or Russia, you will find all universities, they are having that kind of course. So you can understand what is the interest. Okay. Second constraint, that's what we are not having, say, ongoing projects, or we are not developing our engines here in India. And that's what is putting constraints in terms of job prospects. But at the same time, all these MNCs, they are having their centers here in India. Okay, so maybe if you are having your expertise in this particular domain, you have some knowledge, they people will be happy to hire you. I think I am able to convey you what you are looking for.
Yes, sir. Thank you, sir.
Yes, any other participant having any question? Yes, anyone having any query or question? Okay then, so on behalf of Mechanical Engineering Department ADIT, I thank Dr. Chetan Mistry sir, Assistant Professor at IIT Kharagpur, for delivering such a wonderful talk. Thank you very much, sir, first for accepting our invitation and then explaining things so nicely that why CFD is important in, say, supporting such measurement facilities and the other experimental facilities as well. The case studies that you have discussed were really good, sir, and it will help our participants. So thank you very much, sir, for giving your valuable time to us.
Thank you. Thank you very much for all your efforts and inviting me. And secondly, you know, like, it's always required. This students or maybe PG student, UG student, they always are having this kind of interest. But you know, like, in order to understand that part, this kind of programs, they are always required. That's the reason why, without hesitation, I say yes, I will be. Okay.
Thank you. Thank you, sir.
Thank you. Thank you very much. Thank you to ADIT. Thank you to Dr. Thakkar. Okay.
Thank you, sir.
And those who are interested, really interested in working this kind of domain, you are most welcome. We can have interaction. Physically, it is not possible at this moment at IIT Kharagpur for doing some kind of work because students are not around. But yeah, in future, we can explore the possibility for working.
Okay, sure, sir, sure.
Yeah. Thank you. Thank you very much.
Thank you, sir. Yeah.
So here I'm living with.
Yeah, sure, sir. Yes. Okay, okay. To our participants, our next session will start at 2:30 p.m. Thank you, everyone.